Good morning, everyone. My name is Ileana Ielo, and I am from the Department of Chemical, Biological and Pharmaceutical Science in Messina University. Today I will be presenting on biopolymeric nanocomposite for carbon dioxide capture. This presentation is based on a review of recent studies in this field. We are all aware of the critical challenge of climate change. Carbon dioxide is a major contributor to the greenhouse effect, driving global warming. Therefore, capturing CO2 from industrial and power generation processes is essential to reduce emissions and mitigate climate change. Biopolymeric nanocomposites have emerged as promising materials for this purpose due to their renewable nature. Our primary goal is to explore recent studies on biopolymeric-based materials employed for CO2 capture strategy. This involves delving into the latest advancement and approaches in this rapidly evolving field. Secondly, we aim to provide a comprehensive overview of composite materials enriched with nanomaterials. Our focus is specifically on four crucial biopolymers: cellulose, alginate, chitosan and carrageenan. These materials are of particular interest due to their renewable nature and unique properties. Thirdly, this review will examine the preparation methods and the efficiency of biopolymer-based adsorbents and membrane materials. Understanding how these materials are synthesized and how effectively they perform is vital for their practical application in CO2 capture technology. And finally, we hope to demonstrate and highlight the pivotal perspective role of biocompatible and sustainable biopolymers in CO2 capture, storage and also reuse strategies. We believe that these materials offer a promising and environmentally friendly path forward in mitigating climate change. What are biopolymeric nanocomposites? These are materials that combine biopolymers which are naturally occurring polymers from biological sources with nanofillers. These nanofillers are added to enhance the properties of the biopolymer matrix. Common biopolymers include chitosan, cellulose and carrageenan, while nanofiller can be nanoparticles or nanotube or graphene-like materials. One of the most studied technologies in carbon capture and storage involves capturing CO2 from sources like power plants and industrial facilities, transporting it and then trapping it in underground geological formations such as exhausted oil fields or saline aquifers, preventing its release into the atmosphere. There are three main methods for CO2 capture and storage: post-combustion capture, where CO2 is captured after the fuel combustion process, pre-combustion capture, where carbon dioxide is captured before it's released into the atmosphere, and oxy-fuel combustion, which involves burning fossil fuel using pure oxygen and recycled flue gas instead of air. All these methods, however, can be complex and expensive for industrial settings, are beyond these methods. There are eco-sustainable approach. Biological capture using microalgae is a promising avenue. Microalgae have an absorption capacity significantly higher than terrestrial microalgae and can absorb CO2 from photosynthesis, thereby capturing carbon from gas streams, especially in controlled environments like photobioreactors. Membrane separation is another promising technology. It utilizes porous membranes that selectively separate CO2 from a gas mixture, such as flue gas, based on chemical and physical interaction between the gases and the membrane materials. This method offers the potential for lower energy consumption and reduced environmental impact compared to the traditional absorption methods. Lastly, the use of carbon-based materials produced from renewable sources from CO2 capture through absorption and desorption processes is also highlighted. These materials exhibit quick absorption, desorption kinetics, and offers a eco-sustainable low-cost option with their efficiency linked to properties like chemical structure, surface area, and pore size. Understanding these diverse mechanisms and methods is important for advancing CO2 capture technologies globally. Classic approaches like absorption and membrane separation can be significantly improved by advancement in their nanocomposite constituents. Starting with absorption, a key improvement involves the use of biphasic solvents, which are amine alcohol mixture and ionic liquid like imidazolium salts can convert into two phases, facilitating chemical absorption and potentially simplifying the regeneration process for reuse. The anionic part of ionic liquids promotes CO2 absorption, while the cation effect solubility. Next, for absorption, improvements come from selecting and engineering the right materials. We can leverage high porous materials like carbonaceous particles, zeolite, MOF, microporous organic polymers, and amine modified particles. While materials like biochar and carbonized biomass offer cost-effective option, advanced carbon nanotropes such as fullerene, carbon nanotube, and graphene provide superior surface area and enhanced surface chemistry for CO2 capture. For materials like MOF, CO2 capture is further improved by polar functionalization of the pore surface, for instance by grafting OH or NH2 moiety, which allow for tailored CO2 molecule hosting. By focusing on material innovation, we can significantly boost the efficiency and feasibility of CO2 capture technologies. Biopolymeric membranes can be designed with precise molecular porosity. This tailored porosity is what enabled them to selectively separate CO2 from other gas mixtures, such as the nitrogen and the methane, which is critical as flue gas streams. Furthermore, we can significantly enhance both carbon dioxide permeability and selectivity by incorporating functionalized and cross-linked microporous particles into these membranes. This process allows us to create extremely small pores ranging from nano to ultra nanopores, further optimizing this capture efficiency. Cellulose stands out as ubiquitous and sustainable materials. It is the most abundant renewable organic polymer on our planet, naturally biodegradable and non-toxic, making it a highly sustainable choice for environmental application. Its derivatives such as cellulose nanofibrils or nanocrystalline cellulose are mechanically isolated from plant materials, while initially used to enhance the mechanical performance of composites. Their natural properties like hygroscopicity mean that chemical modification is often essential to optimize them for carbon dioxide capture. This chemical modification is a crucial enhancement strategy. It typically involves the incorporation of organic or of inorganic nanoparticles or the functionalization of cellulose inherent hydroxyl group with aminosilane. These promote CO2 chemisorption, allowing for efficiency CO2 binding. Notably, the absorption capacity of this modified material can even increase proportionally with the humidity, indicating favorable interaction with water molecule, as seen with modified carbon nanofibril aerogels. Such modification have led to impressive absorption capacities, with some composites achieving up to 5.5 millimole per gram. Beyond absorption, cellulose also play a vital role in membrane technology. Cellulose acetate membranes, often coated with materials like polydimethyl siloxane or combined with functionalized multi-walled carbon nanotube and various additives, have demonstrated excellent selective separation of CO2 from other gas like methane and nitrogen. This highlights their versatility in different capture application. However, it's important to acknowledge some challenges and disadvantages associated with cellulose. It often exhibits poor solubility in many common solvents, which can complicate processing. It also has limited thermal stability and can be susceptible to microbial degradation under specific environmental conditions. Furthermore, the industrial synthesis and modification processes can sometimes involve high energy consumption costs. These biopolymers, in particular alginate and chitosan, possess unique properties that make them ideal for CO2 capture. Alginate is a hydrophilic, biodegradable and non-toxic polysaccharide characterized by abundant carboxyl and hydroxyl groups, which are key for chemical reactivity and material fabrication. Chitosan, on the other hand, is known for being biodegradable, biocompatible, and for its antimicrobial properties. Crucially, it contains numerous nitrogen-containing amine groups. A particularly powerful approach is their synergistic combination. Alginate and chitosan are often used together, leveraging their complementary electrostatic properties to create material with increased stability and durability. In the context of CO2 captures, their applications are diverse and effective. In membranes, alginate hydrogel have been successfully used to prepare robust MOF composite fiber membranes, demonstrating excellent separation ratio for gases like hydrogen and carbon dioxide. As adsorbent, these biopolymers show significant promise. Examples include ammonia functionalized alginate beads with enhanced CO2 absorption and amine functionalized silica combined with alginate for efficient CO2 removal. Chitosan coated mesoporous silica exhibit high absorption capacities and crucially excellent recyclability and relative low temperature, making them highly valuable for CCS technologies. We also see high absorption capacities in chitosan grafted graphenoside aerogel and even in carbon spheres derived from both alginate and chitosan, achieving up to 5 millimole per gram, owing to their inherent nitrogen content and microporosity. Furthermore, alginate and chitosan are excellent materials for enzyme immobilization, particularly from carbonic anhydrase, but working with the enzyme can be tricky because they are fragile, sometimes expensive, and they can be hard to separate from your reaction mix once they've got done their job. That's where enzyme immobilization come in. It's basically giving our enzyme a home to live, so we can reuse them, protect them, and make them work better in industrial settings. Let's look at 4 main ways we do this. First, we have absorption. Think of this as simplest method. We basically just take your enzymes and let them stick or absorb onto a solid surface like a bead or a particle. It's like putting a sticky note on a whiteboard. They adhere through weak physical forces. The great thing about this is super easy to do, often doesn't require any harsh chemicals, and usually doesn't mess with the enzyme activity much. The downside, those weak forces mean that they can sometimes fall off or leach out over time. Next, we move to surface covalent bonding. This is a more robust approach. Instead of just sticking, we create strong chemical bond directly between the enzyme and the surface of a support material. Imagine tying your enzyme securely to a scaffold. This makes the enzyme really stable and prevent it from leaching away. The trick here is to make sure those chemicals bond don't accidentally mess with your enzyme active site, which is the part that does all the work. It requires a bit more chemical know-how, but the stability is a huge advantage. Then we have encapsulation within a polymer. For this one, picture trapping your enzyme inside a tiny polymer cage or a gel-like matrix. It's like putting them in a mini jelly bead. Materials like alginate and chitosan, which we just discussed, are excellent for this. They create a protective microenvironment for the enzyme, shielding it from harsh condition or contaminant in the surrounding solution. This is fantastic for protecting delicate enzyme. And the main challenge can be making sure the molecules you want the enzyme to act on, like CO2, can easily diffuse into the cage and the product can diffuse out. And finally, cross-linking. This method is a bit different because it doesn't necessarily use an external support. Instead, you use a special chemical cross-linker to link to the enzyme molecule directly to each other, forming larger insoluble aggregates. This of it thinks of it like connecting a bunch of Lego bricks together to form a bigger solid structure. This gives you highly stable, reusable enzyme preparation without needing a separate support material. The main concern here is making sure that the cross-linking process does not cause the enzyme to lose its shape or activity. However, like all materials, they come with certain challenge. They can exhibit limited mechanical strength, which might affect their durability in demanding applications. There also a possibility of enzymatic degradation over time, and their solubility and gelation condition are highly dependent on pH, requiring careful control during material synthesis and application. Despite these points, the outlook is very positive. These chitosan and arginate-based materials possess excellent properties for the reversible absorption of CO2, further improved by appropriate chemical modification. The last polymer is a natural polysaccharide extracted from red seaweed, known for its unique sulfate sugar units. While traditionally used in food and pharmaceutical, researchers are increasingly exploring its potential in environmental application like carbon dioxide capture. One key advantage of using carrageenan, especially when compared to direct microalgae systems, is its protective capability. However, it's also important to consider, also in this case, a disadvantage, and they have a limited mechanical strength, which might impact its long-term stability in certain applications. It can also be susceptible to enzymatic degradation, and also its gelation conditions are quite sensitive, depending not only on pH, but also on the ionic strength of the solution. In conclusion, we have seen that diverse biopolymers such as cellulose, alginate, chitosan and carrageenan offer unique inherent properties, which are significantly enhanced through targeted chemical modification and smart integration of various nanomaterials. This synergistic approach allows us to tailor their performance for specific capture needs. Thank you for your kind attention.